solubility. To first understand how one compound dissolves in another, we can now take a look at how two compounds interact when they are actually being mixed together. So in this example here, we are now mixing compound 1 with compound 2. And F1 is the intermolecular force in compound 1, while F2 is the intermolecular force in compound 2, while F3 is the interaction force between compound 1 and compound 2. Compound 1 to dissolve in compound 2 or vice versa, F3 must actually be comparable to the force in F1 and F2. So let us give an example. So if we were to put oil and water together, say H2O is your compound 1, and your oil, which is your alkane molecule, non-polar, is compound 2. In this case, we will note that F1 will be the strongest intermolecular force relative to F2 and F3, since F1 is intermolecular hydrogen bonding, while in the case of F2, it's just relatively weaker IDID. And obviously, F3 will also be instantaneous dipole-to-dipole attraction forces. Hence, because of this, if F1 is actually the strongest, then the water molecules will prefer to stay together and not mingled with compound 2 or the oil molecules. Hence, water and oil does not dissolve. Conversely, if we now change water to, say, vinegar. So in the case of vinegar, is your ethanoic acid. So ethanoic acid has the OH group, which can form intermolecular H bond as well. So F1 is intermolecular H bond, F2 is intermolecular H bond, similarly F3 as well. And therefore, because of this, since F1, 2, 3 are all comparable in terms of the strength of the intermolecular force, all the molecules could form and break and mingle together. So in this case, vinegar or ethanoic acid will be able to dissolve in water. So with this understanding, we now start off by looking at non-polar solvent. For non-polar solvent, they would not be able to dissolve polar covalent molecule, primarily because the interaction forces between the non-polar and the polar covalent molecules could be PD, permanent dipole to induced dipole, or otherwise instantaneous dipole to induced dipole, but they will be relatively weaker than the permanent dipole to permanent dipole attraction force amongst the polar covalent molecule. So the polar covalent molecules prefer to stay on their own. On the contrary, non-polar solvent will be able to dissolve non-polar solute. So in the case of C7H16, your heptane, and your C8H18 octane are able to dissolve very well with each other. The reason is because the interaction force that they form between each other is instantaneous dipole to induced dipole attraction force, which is actually comparable to the IDID that's within the heptane molecules or within the octane molecules. So they're actually comparable in strength. Finally, if you look at the polar solvent firstly will be able to dissolve ionic compound very well because it can form ion dipole attraction force. Bear in mind that ion dipole attraction force is stronger than ionic bond. Therefore, NaCl will be the most soluble in water. Next will be your carboxylic acid, or in this case, your ethanoic acid. Because in the case of ethanoic acid, they could form extensive hydrogen bonds with water molecules, as the ethanoic acid have the C double bond O group, which can form H bond with water molecules, and also the OH group, which can also form H bonds with water molecules. Finally, if you take a look at the CHO, that will be the next most soluble, is that you will find that CHO can form a combination of both intermolecular PD-PD and intermolecular hydrogen bond. I'd like to highlight here that this is actually a hydrogen bond because these two hydrogen atoms are electron deficient or protonic since they are bonded to the highly electronegative oxygen. While the hydrogen atom that's bonded to the carbon in your HCHO is not electron deficient, so therefore it could only form intermolecular PD-PD with the water molecules. Finally, H2S is the least soluble in water because in this case they can only form PD-PD attraction forces with water molecules, all right, and therefore less able to compensate for the energy required to overcome the intermolecular hydrogen bonds between water molecules.